All right, practice exercise number 20. As we get started, you may use your calculator, just 4 questions. And your calculator can help you navigate those fractions. So we just worked add, subtract, multiply, divide in 4 different exercises. Now you get to figure out, what do I do? Do I add, subtract, multiply, divide? Let the calculator do the work. Go and get started. Once you finish, pencil down. Look this way so I know you're done. Let's go and take a look at these together. And Abby, I believe, was first. Abby says Jordan feeds her dog 4 1/3 cups of dry dog food each day. She gives 2 1/2 cups in the morning and the rest in the evening. How many cups of dog food does she give her dog in the evening?
1 5/6.
Good. All we have to do is enter 4 1/3 minus 2 1/2, and you get 1 5/6 cups of dog food. All right, for the second one, a bag of dog food lasts Jordan's dog 12 days. How many cups of dog food does the bag contain? 52. All we have to do is take the 4 1/3 cups a day times 12 days, 52 cups of dog food. For the next one, Mike's dog eats 2 cups less than twice as much as Jordan's dog. How many cups of dog food does Mike's dog eat each day? 6 2/3. We take what Jordan feeds her dog, 4 1/3 times 2, but then we subtract 2 cups from that to get 6 2/3. Presumably, Mike's dog is bigger, or it's just fatter because it eats too much. I'm not sure which. Let's go with bigger. It definitely weighs more. It says Mike's dog weighs 61.5 pounds. Jordan's dog weighs 48 7/8 pounds. How many more pounds does Mike's dog weigh than Jordan's dog? 12 5/8 pounds is correct. Nice catch. Anyone else perfect 4 for 4, just like Abby, just not as fast. All right, questions on the exercise.
This one should be graded.
I'm sorry, question?
I was just confused how you got 52.
You multiply, because in the first problem it says 4 1/3 cups each day, and the bag lasts 12 days. So you could do 4 1/3 plus 4 1/3, over and over again, but 4 1/3 times 12. All right, good. All right, I'm going to pass those forward if you would, please. Take your homework handouts out. Handout 11 looks something like this, only it should be completed at this point, so pass the exercises forward. And once those are in, once you've passed yours in, go get the homework handout out. And we'll take a look at it together. Homework handout out. And we have this picture that you were given, or something like it at least. It was just kind of sketched very quickly. I think it was drawn a little more carefully on the handout. And we were told that these two lines, AC and BC, are equal. We were also told that AO and BO bisect angle A and angle B, respectively. So we've got these two angle bisectors that meet at a point called O, and then from this intersection of the bisectors, it goes up to C. Go ahead. All right, so the question is, when we draw the line from O back up to C, does that make equal angles, or prove rather that it does make equal angles X and Y? All right, so your first statement, obviously, you would have just written what, Brecken? I'm going to abbreviate respectively for sake of time. All right. Now, number 2, you remember yesterday we were looking at a problem where we had two different angles and they were both bisected, right? And so I told you if you have one angle that's bisected, just say you've got two equal angles. But if two angles are bisected, I encourage you to specify that you have not just equal angles at each bisector, but equal halves. And that's what I had you, or what I put down there in number 2. Angle 1 and angle 2, right here, yes, they're equal to each other, but they are specifically halves of angle A. And similarly, angle 3 and angle 4, well, yes, they're equal, but they're not just equal, they're equal halves of angle B. What is the reason here for this statement? What did you put, Lana?
I put halves of equals are equal, but that's not right.
It's not. How do we know that these are halves? How do we know that these are equal? Has to be something from the given, because we haven't had anything else yet. It's got to be something from the given.
Because AO and BO bisect?
Because AO and BO bisect, and that's... Josh?
Definition of an angle bisector.
Yeah, what is the definition of an angle bisector? A line that divides an angle into two equal halves, two equal angles, both of which are half of the whole. So that's just the definition of an angle bisector. How many had, for your reason, definition of angle bisector? Leave your hand up for just a second. All right, most of you, good, all right. So again, just think of that definition, that clang word bisect. But again, one angle bisect, clang, these two parts are equal. Two angles bisect, you're gonna be better off by saying clang, we got equal halves of the original angle, because number 3, there was another clang statement in the given. What was the other clang statement in the given, Noah? We already hit up bisect. That's a clang word. It's not so much a clang word as much as a clang. Yeah, AC and BC are equal. Now, if AC was a line over here and BC was some line over there, big deal. But they're not just two random lines. AC and BC, Noah, are two lines that are in a triangle, the big triangle ABC. And if in a triangle, again, ignore the noise in the middle. If AC and BC are equal, Noah, clang. Which angles? The opposite angle. So again, ignoring the noise in the middle, what angle is across from BC, Noah? Angle A. And what angle is across from AC, Noah? So what should we state for number 3? Angle A equals angle B. And the reason that you, how many had angle A equals angle B for number 3? All right, Josh, what was your reason?
In a triangle, equal angles opposite sides are equal.
I think you mean angles,
Well, angles
opposite equal sides are equal. Okay, so a little bit on the wording there. Angles opposite equal sides in a triangle are equal. Now here's the big kicker. 1 and 2 are halves of A. 3 and 4 are halves of B. But A and B are equal. So 1 and 2 and 3 and 4 class are halves of equals. And what do we know about halves of equals, Lana? What do we know about halves of equals, Lana? They're equal. So if 1, 2, 3, and 4, if they're all halves of equals, class, then number 4, and I stated this, class? Yeah, 1 equals 2 equals 3 equals 4. They're all equal to each other because, what was it again, Lana? Halves of equals are equal. So I've incorrectly marked them then. Based on what I knew then, these two are equal halves of this, these two are equal halves of that, but because they're all equal to each other, I'll just let them all be marked with single tick marks here. Questions on this? Do you see the significance of saying you had halves? That allowed you to get all 4 little pieces equal to each other at once. Questions? All right, all of that so far has pretty much been clang, and then, well, if these are halves of these and these are equal, then halves of equals are equal. We really haven't taken time to consider what we're trying to prove. We're trying to prove x and y are equal. We're trying to prove we have 2 equal angles, right? We had 2 ways to get angles equal. There was a little box, remember yesterday? Said ways to prove 2 angles are equal. Give me one of those ways. Adam, do you remember? Brandon?
Well, I know both, but CPCTE.
Okay, CPCTE, if we had congruent triangles, what was the other way to get angles equal? Michael?
I don't know.
We could get triangles congruent, use CPCTE. What's another way to get just a couple of angles equal to each other? Brandon, go 2 for 2?
Sides opposite equal angles are equal.
If we were in the same triangle and they were opposite equal sides. So if I looked at these 2 angles, I was like, how do I get those 2 angles equal? If I can get the opposite sides equal. But if I have 2 different triangles, I'm like, how do I get those 2 angles equal? Oh, well maybe they could be corresponding parts of congruent triangles because they're in 2 different triangles. Does that make sense? Well, x and y, are they in the same triangle or x and y in different triangles? That's the question. Back to Adam. Are angle x and angle y formed within the same triangle or are they in different triangles? They are. You might say, well, no, they're both in angle ABC. X is not an angle of triangle ABC. And y is not an angle of ABC. Y is in this little triangle. X is in this little triangle. So since they're in separate triangles, class, what's our strategy? Triangles congruent? CPCTE. So somehow, some way, I know somewhere down here, I'm going to want triangle AOC to be congruent to triangle BOC. If I can get these 2 triangles congruent, I know that angle X will equal angle Y, class, by CPCTE. Now again, do you have to write it down low necessarily? No, you don't have to. But the point I'm making is you already know how this proof ends. The question is, how do you go about getting AOC and BOC equal? Okay, so Lana says I got side angle side. What sides, what angles do we have equal? Because side angle side's an option, right? Side, side, side's also an option. Angle, side, angle's also an option. So we've got options, right? Lana, you said you went side angle side for your reason. What sides do we already have? Again, the 2 triangles I'm looking at are this guy here and this guy here. What sides do I already have equal? AC and BC. Right here in the given, there's a pair of sides that I already have equal. All right, do I have any other sides already equal to each other? Noah? Okay, CO and CO could be equal to itself. So we could state CO equals CO, equal class by identity. Now, if I'm trying to go side angle side class, what angles would have to be equal? X and Y. Side angle side. Well, if I already had X and Y equal, I don't need congruent triangles, do I? So if I'm going side angle side, it ain't these two angles, so it ain't these two sides. But CO could equal CO. That could be a thought, but it won't get us side angle side. Do we have any angles equal yet? Any angles equal yet? Dylan?
1, 2, 3, 4.
Okay, 1 and what? Well, specifically though, I'm just looking at the blue and pink triangles here, or the shaded triangles. The fact that 1 and 4 are equal, right? There's a pair of angles. Okay? Now again, this would be side angle, but the side's not right next to it, right? If we try to go Lana's idea of side angle, what sides would have to be equal, class? AO and BO would have to be equal. Well, let's suppose we didn't go with Lana's idea. Let's suppose we try to go angle side. Oh, we're back to X and Y again. Okay, I'm going to rule angle side angle out. Or maybe we decided to go side, side, side. Do you see no matter which route we go, class, we need AO and BO equal? Either for side angle side or side, side, side. Question, how could I get AO and BO equal? Well, we had a box in our text yesterday that said how to prove two lines are equal. One way, class, was to get congruent triangles and use CPCTE. And that kind of shoots that out. The other way was if the two lines were in the same triangle, class, showed that the opposite angles were equal, right? Well, AO and BO are in two different triangles. Congruent triangle CPCTE could work, except I kind of need that for the congruency. But AO and BO are also in the same triangle, aren't they? And what angle is opposite AO, class? What angle is opposite AO? 3. Okay, I thought I heard 2. What angle is opposite BO? 2. And what do we know about 2 and 3? They're equal already. So since 2 and 3 are equal, class, what is true about AO and BO? They're equal already. AO equals BO because, how can I write the reason here, Michael?
Sides opposite equal angles.
Good. Sides opposite equal angles. 3 little words. In a triangle are equal. Or you can put the inner triangle at the beginning, it's fine as well. And if AO equals BO, well, I got sides right here. I got angles right here. I got sides right here, so we can use side, angle, side. Now, what if you didn't want to do side, angle, side? Would it be wrong to state, number 6a, that CO equals CO by identity? In which case now, class, I have side, side, side instead. Would that be wrong? It takes one extra step, that's all. But it's not wrong. Now, I kind of tied you in a box by only giving you the 7 statements and reasons. But you could have squeezed a CO equals CO and a side, side, side. Did anyone do that? You went CO equals CO, you went side, side, side. How many just rolled with this? Anyone's proof perfect based on how I put it together for you?
Oh, I did.
Okay, questions on the proof now that we've done it together. Does it make sense now? Even if you didn't get it last night, do you follow the proof? Do you see, by the way, the 2 ways to finish it? Do you see that side, side, side is a viable option here? All right, questions. How many said side, angle, side, but you were thinking these 2 sides and these angles, and you never got the AO and BO equal? So you technically had side, side, angle instead of side, angle, side. We're actually going to address side, side, angle. Let me move the screen over here. And Gavin, you'll notice we have side, side, angle marked here and crossed out because a lot of students will see side, side, angle and they'll try to say, oh, that means triangles are congruent, and it doesn't work that way. So we'll explain why it doesn't a little bit later on, but all right, but that's an easy mistake to make. It's certainly something I've seen a lot in my years of teaching. Questions? Any questions on this? All right, let's set that aside if you would, please, and take out your notebooks, turn to the terms definition section. Notebooks out, terms definition section. I promised Michael I would teach something today, and we're going to teach it today. Next thing, in your notes, let's talk about parallel lines. Terms definition section. Parallel is spelled P-A-R-A-L-L-E-L. But it's the only time all year you're ever going to write the word out. Because you don't want to lose points for spelling by accidentally putting 2 R's or 1 L. No! The rest of the year, if you want to write parallel, you're going to put a tall, skinny 11. That's the symbol for parallel. So parallel lines. Go and put that shorthand there so that way we can use it later. Parallel lines. Here's your definition. Lines in the same plane. Lines in the same plane that are everywhere the same distance apart. Lines in the same plane that are everywhere the same distance apart and therefore never intersect. Lines in the same plane that are everywhere the same distance apart and therefore never intersect. Now, some of you have already had Algebra 2, and you've talked about asymptotes in Algebra 2. And you're like, well, if you have an asymptote, the line doesn't intersect the asymptote. Well, technically, you'd be dealing with a curve there, not a line, but that's kind of one of the reasons. Also, if you have a straight line here and a straight line here, they aren't necessarily parallel, but they never intersect. But they're also not in the same plane, right? So lines in the same plane that are everywhere the same distance apart, and therefore never intersect. Once you have that written down, that's a definition. How many are already kind of familiar with parallel lines? They don't cross. Okay, already familiar with that idea. Turn to the theorems postulates section. We want to add a postulate here to our lineup. Postulate 6. Postulate 6. This is referred to, by the way, if you want to put this in your notes, this is the parallel postulate. The nickname of postulate 6, the parallel postulate, or Euclid's parallel postulate. Postulate 6 says this: through a given point, one and only one, straight line, through a given point, one and only one, straight line, may be drawn parallel to a given line. Through a given point, one and only one, straight line, may be drawn parallel to a given line. Through a given point, one and only one, straight line may be drawn parallel to a given line. You can't prove it. Okay, we proved, based on other axioms and postulates and definitions, that only one perpendicular could be drawn to a line. We proved that only one perpendicular could be drawn at a point, but you can't prove that there's only one parallel. How many would say if I drew the line here, that would be parallel? It doesn't appear to be so, does it? But if I got a line, maybe, does that right there kind of look parallel? Now, if this is the parallel, any other line I draw would not be perfectly parallel, correct? At some point, if this one doesn't intersect, any other line I draw would at some point intersect. Would we agree? But we can't prove it. So we'll say, let's accept this as true, because you can't demonstrate another line, a separate line drawn through here that doesn't intersect. I mean, you can see any other line at some point is going to intersect that line if extended far enough, right? But there is one line you could draw, but only one, and that's postulate 6. Any questions or contesting postulate 6? All right. If we accept postulate 6, there's another statement that follows logically. We're going to call this Postulate 6 Corollary 1. Postulate 6 Corollary 1. This is the parallel postulate corollary. The parallel postulate corollary. If you accept that you can only have one parallel through a given point, then you must admit the truth, and we'll prove this then, that lines parallel to the same line, lines parallel to the same line, lines parallel to the same line are parallel to each other. Lines parallel to the same line are parallel to each other. Lines parallel to the same line are parallel to each other. Here's the idea. Here is line. Okay? And let's call this A, and let's suppose we know, well actually let's name it X. Okay, so let's suppose we know that A is parallel to X. Let's draw another line right here, and let's say it's B. Now, I'm just looking at it. My eyes tell me it doesn't look parallel, okay? But we don't trust our eyes. Let's suppose we knew that B was also parallel to X. Imagining I drew it more accurately than that, and I actually used the straight edge, which might have been a good move, if they're both parallel to X, doesn't it kind of make sense they're parallel to each other? But this isn't a postulate because it's provable. If we've accepted that through a point, you can only have one parallel, imagine for a moment with me that these are not parallel. They're both parallel to X, but they are not parallel to each other. Indirect proof, right? Well, if they're not parallel to each other, class, then what would have to happen at some point? They would intersect, right? So at some point, if you drew the lines out far enough, they'd intersect somewhere, wouldn't they? I mean, this is kind of exaggerated. It'd be way out there in space somewhere. But eventually, if they're not actually parallel to each other, they would intersect at some point, call it P, okay? But they're both parallel to X, right? Two lines can be drawn parallel to the same line through a given point? No, we just accepted that through a given point, you can only have one parallel. So if that's true, two lines parallel to the same line will never intersect at a point, or that would violate the parallel postulate. Therefore, if lines are both parallel to the same line, they must be parallel to each other. Does that make sense? So kind of an indirect proof thought. But again, not actually a postulate, because this was provable. All right, indirectly at least. All right, questions on that? Yes, sir.
Can you say that one more time?
One more time. Lines parallel to the same line. Lines parallel to the same line are parallel to each other. Lines parallel to the same line are parallel to each other. I will say this, I feel like the parallel postulate corollary, just in doing the indirect proof, strengthens the affirmation that the parallel postulate must be true. Because as you see that, it is like, yeah, that's true. Because if they weren't parallel to each other, but they've got to be parallel, so it kind of strengthens the belief, at least. The blind belief, one could argue, I suppose, not entirely blind, but unprovable belief that the parallel postulate is true. But questions on these? All right, so a term and a couple of postulates, or rather a postulate and a corollary there. Let's go back to terms definitions. Was that a hand?
No.
Okay. All right, parallel or terms definitions section of your notes. We're going to get this term down in your notes, transversal. Transversal. We'll abbreviate it transv, because it's the only word that we'll use this year that starts with transv. All right? So transversal. We know what the prefix trans means. In fact, we hear it, frankly, way too much in our culture today, don't we? But what does it actually mean? The root or the prefix trans? Across. It means across. So the idea with a trans person, for instance, right, is somebody who's gone across the gender gap. And they now, I feel like I'm a woman now. Right, whatever. But anyway, we're not going to get off on that. All right, that would take way too much time. But trans just means across. So if you have a couple of lines, and there's a line that goes across to other lines, now we don't just have an intersecting line, but we have a line that creates two different intersections. This line is called the transversal. So your definition is a line that intersects two or more other lines. A line that intersects two or more other lines. A line that intersects two or more other lines. Now, once you've written that in your notes, if you have about 5 or 6 lines left on the page at least, if not, go to the next page. But if you've got at least 5 or 6 blank lines still on the page, go ahead and draw a couple of lines and go ahead and draw a transversal. Label the transversal T. We're going to use a picture to define some of our terms now, simply because in words it would be very time-consuming and frankly not as helpful to you in your studying. Once you've drawn this, what you should have is 4 angles at this point of intersection and 4 angles at this point of intersection. Let's number these 1, 2, 3, 4, 5, 6, 7, 8. So go and number the angles 1 through 8. You'll notice that angles 1, 2, 7, and 8 all lie to the outsides of the lines, correct? So if you write this down, angle 1, angle 2, angle 7, and angle 8 are called exterior angles. Not exterior angles of a polygon, but exterior angles of the lines. Okay, so 1, 2, 7, and 8, those are exterior angles because they're on the outsides of the lines. Anyone want to hazard a guess at what we would call angles 3, 4, 5, and 6? Since they're in between the 2 lines, class. Yeah, very good. So angle 3, angle 4, angle 5, and angle 6 are referred to as interior angles, since they are formed between the 2 lines. So if you've got 2 lines intersected by a transversal, you have exterior angles and you have interior angles. Pretty straightforward, right? I want you to notice this. Look at angle 2. It's exterior, as is 1, 7, and 8. Notice 7 is also exterior, but notice that while 2 is on this side of the transversal, 7's on that side of the transversal. So they're exterior to the lines, and they're on what we call alternate sides of the transversal. Those are referred to as alternate exterior angles. Alternate exterior angles. And there's 2 pairs of them, angle 2 and angle 7. And of course, angle 1 and angle 8. So when exterior angles are formed, they're formed in 2 pairs of alternate exterior angles. 2 pairs of alternate exterior angles. 2 and 7 are alternate exterior, 1 and 8 are alternate exterior. You could do the same thing with your interior angles though as well. For instance, notice number 3, number 6. They're interior, but they're alternate sides of the transversal. So we could say, and I'm going to abbreviate alt, int, angles. Angle 3 and angle 6 are alternate interior angles. Of course, there is one more pair of alternate interior angles, class.
4 and 5.
Angle 4 and angle 5. Angle 4 and angle 5 are also alternate interior angles. Do we get the idea of what alternate means? Alternate sides of the transversal. So alternate interior, they're both interior, but they're alternate sides. Alternate exterior, they're outside, they're exterior, but they're on alternate sides. Questions on alternate interior or alternate exterior? There's one more way in which we can pair up angles, and I'm going to go ahead and give myself a little bit more board space here. Oop, didn't mean to erase the number. Might have been quicker to draw me a picture. I'm not sure. All right. I want you to notice this. Look at angle 2. Notice where it is. It's above its respective line, and it's to the right side of the transversal. Do you notice that angle 6 is in a similar position, where it's above its respective line and to the right side of the transversal? They're in matching positions, but we don't use the word matching in geometry because it sounds too boring. We use a fancy word for matching, even with congruent figures. Corresponding. So corresponding angles, again, not of congruent figures necessarily, but here when lines are intersected by a transversal, corresponding angles would be angles like angle 2 and angle 6. Of course, it's not the only pair. Look at angle 4. Do you see how it's also on the right side, but it's below its line? 8's in a matching position. So angle 4 and angle 8 would be corresponding angles as well, because they're in matching positions. Right, south, southeast, if you will, if you want to use north, south, east, west. These are northeast, those are southeast. What would be the corresponding angle to angle 1, class? Angle 5 is in that matching position, isn't it? So we could also say angle 1 and angle 5. And of course the last angles, class, 3 and 7, are going to be corresponding angles as well. Questions on this terminology? Again, rather than giving you definitions in words, I think the picture helps more for you to see how these angle pairs are formed. Questions on that? All right, now that we have a baseline understanding of what these things are, what are parallel lines, what is a transversal, what are these pairs of angles, let's go to the theorem's corollary section and let's apply some of these facts that we've learned. I have those who had me in 8th grade, which I guess in this case are just Lana and Josh. We looked at this in junior high math, so something you've already seen, the rest of them may or may not have seen. So in other words, you might have a leg up on some people for a change. All right, Theorem 7 in your notebooks. Theorem 7 says this: if, comma, when two straight lines are cut by a transversal, if, comma, when two straight lines are cut by a transversal, comma, if, when two straight lines are cut by a transversal, a pair of alternate interior angles are equal, comma, there's all kinds of little subordinating things here. If, when two straight lines are cut by a transversal, a pair of alternate interior angles are equal, comma, then the lines are parallel. If a pair of alternate interior angles are equal, then the lines are parallel. If, comma, when two straight lines are cut by a transversal, comma, a pair of alternate interior angles are equal, comma, lines are parallel. Lots of commas. One more time through. If, when two straight lines are cut by a transversal, a pair of alternate interior angles are equal, then the lines are parallel. All right, once you got that down, turn to the proofs of Theorem's corollary section, and on the top of a new sheet of paper, put Theorem 7, and we're going to abbreviate it this way. Equal alt int angles lead to parallel lines. Equal alternate interior angles produce, lead to, give parallel lines. Equal alternate interior angles lead to parallel lines. That's what we'll put at the top of the page, kind of shorthand there for you. If you would, go ahead and draw a couple of lines that, to the best of your ability, appear to be parallel. Now, this should be really easy because you have lined paper, okay? So don't make this hard, okay? Draw a couple of lines that, to the best of your ability, appear to be parallel. Call the one MN, and call the other XY. Now, we don't know that they're parallel. We're going to prove that they are, but it would help if I could see that they look parallel, okay? So even if you didn't have lined paper, as I don't, and even if they're not perfectly parallel, it's okay. We don't trust our eyes. Draw a transversal, if you would, running right through them, and let's call it RS. RS. And we should name the points of intersection here. Let's call this point A, and we'll call this point B. Should have gone with I could have made it ribs. Anyway.
It's a ram.
Crabs. Anyway. All right.
Man.
Anyway.
Man.
And ram.
Man. All right. Anyway.
Ram.
So, what are we given? Well, we're given if when two straight lines are cut by a transversal. Okay, let's start with that. We have two straight lines cut by a transversal. Given RS intersects MN and XY at A and B, respectively. Given RS intersects MN and XY at A and B, respectively. So that's the first part of the theorem. If when two straight lines are cut by a transversal. Well, it was just given that two straight lines were cut by a transversal. But it didn't stop there. It says, if when two straight lines are cut by a transversal, a pair of alternate interior angles are equal. Well, since B is in the way of this angle, I'm going to call this angle 1, and its alternate interior angle will be this one, which I will call angle 2. We'll be given that a pair of alternate interior angles are equal. So, angle 1 equals angle 2. If, when two straight lines, MN and XY, are cut by a transversal, RS, a pair of alternate interior angles are equal, angle 1 and 2, then the lines are parallel. So we're going to prove that MN is parallel to XY. We're going to prove that MN is parallel to XY. Now think about what that means. Parallel class means that they never intersect. Is that going to be a little challenging to prove that they never intersect? It's hard to prove never, isn't it? It's easier to say, okay, well, show me a time where they do. Show me one instance where it is true. So I think here's a great opportunity, again, to use the indirect method of proof. So you do not need two columns, statements and reasons. This does not exist. You only think it does. So if you would, statement number 1. Again, you don't have two columns, statements and reasons. We'll go ahead and start with the given, though. RS intersects MN and XY at A and B, respectively. Cheating and abbreviating, even though it's not official shorthand. It's also not a term, so we don't really care. All right, angle 1 equals angle 2. All of that is given, so we know that's all true. That's the conditions of the proof. If we're going to approach this with the indirect method, what has got to be statement number 2? Dylan? So, what do we write? Assume what? Good. Assume MN is not parallel to XY. All right. You thought those lines were parallel? They're not parallel. And if they're not parallel, then what must be true, class?
They do intersect.
They must intersect somewhere. Now, they don't intersect on the page or on the chalkboard yet, but you understand if I extend them, they will intersect, correct? So if I just extend this line out here somewhere, and I extend this line out here somewhere, eventually they'll intersect. And you say, well, those don't look like straight lines. No, they are. You just don't trust your eyes, okay? Those are straight lines. Okay? Really what I'm trying to do is I can't go out into the hallway and into Miss Morris's room and out into the auditorium wall or something just to try to draw this, right? You realize it would be a long way of extended out there, right? But if they are not parallel, eventually you keep extending them, they will cross, correct? The only way they don't cross is if they are parallel, but we're assuming they're not. So number 3, got my drawing in the way, extend MN and XY until they intersect at some point P. That's the name of my point. Eventually, they intersect at a point P. Now again, I know the lines look curved to you, but they really are straight lines, and they're really, really long, okay? That's like way out in space somewhere, okay? Well, think about what I just formed then. A is a point, B is a point, P is a point. And through these 3 points, I've drawn 3 straight lines, correct? So what is A, B, P? It's triangle. Based on the definition of a triangle, A, B, P is a triangle. Now, kind of looks funny here, but you notice how this line, PA, has been extended through the vertex? And there's this little angle out here on the outside of the triangle, correct? What would we call angle 2 with relation to this triangle right here, class? It's an exterior angle. So what do we know about an exterior angle of a triangle? It's greater than the opposite interior angles. Which angles are opposite interior to number 2? Angle 1 and angle P, right? Angle A is adjacent interior, but 1 and P are opposite interior angles. So therefore angle 2 must be greater than either angle P or angle 1. Anyone got a problem with that? Yeah, and to given it said that 1 and 2 were equal. Well, now all of a sudden angle 2 is bigger. Got a contradiction. Where'd it come from? The assumption. The assumption's wrong. Let me say that again and think about the chapel service. If you make an assumption and you arrive at a contradiction later because of the assumption must be wrong. Science. Science. I'll put it in quotation marks. Wrong because of the assumption's been wrong. So yeah, we've got this contradiction right here. And therefore, we can, and then must be parallel to xy. Because to assume anything other than that is to cause a contradiction. So they can't not be parallel. They must be parallel to each other if these two angles are equal to each other. Questions on that? Questions on Theorem 7? So, alternate interior angles are equal, parallel lines. I kind of look at this as one of our foundational proofs. Side angle side was a foundational proof. Once we proved side angle side, we proved a whole lot of other things. Now that we've proved this, there's going to be a lot more things we can prove as well. Some of them are corollaries. So go back to the Theorem's Corollaries section of your notebook, and let's discuss some corollaries. For the sake of time, we won't do the formal proofs of them. I'm going to go give you the corollaries, and I'll talk through the proofs. Just for sake of time. Corollary 7-1, for instance. Corollary 7-1. Says this: if, comma, when two straight lines are cut by a transversal, comma, starts out the same way as the theorem does. If, when two straight lines are cut by a transversal, comma, a pair of corresponding angles are equal. If, when two straight lines are cut by a transversal, a pair of corresponding angles are equal, comma, then the lines are parallel. It's word for word Theorem 7. It just says corresponding instead of alternate interior. So copy Theorem 7 again, but instead of saying alternate interior, put the word corresponding. If, when two straight lines cut by a transversal, a pair of corresponding angles are equal, then the lines are parallel. Kind of abbreviated this way. Corresponding angles are equal, lines are parallel. That's kind of the gist of it. Here's the idea, just for sake of time. We have two straight lines cut by a transversal. I'll make it go this way for a change. And we have this angle and this angle are equal to each other. Corresponding angles, correct? By definition, above the respective lines, both to the same side of the transversal. The question: what is true about, I'll call this angle 1, I'll call this angle 2. Let me call this angle 3. What's true about 1 and 3, class?
They're vertical.
They're vertical. So therefore, angle 1 and angle 3 are equal. We are given angle 1 equals angle 2, right? Given corresponding angles equal, proving lines parallel. Well, if 1 equals 2 and 1 equals 3, class, then 2 equals 3. What kind of angles are 2 and 3? Alternate interior angles. And we just proved if alternate interior angles are equal, class, parallel lines. So therefore, the lines are parallel. If corresponding angles are equal, because through vertical angles you get alternate interior angles equal. Make sense? Corollary 7-2. Write it again, same exact thing, but this time instead of saying corresponding, say alternate exterior. If, when two straight lines are cut by a transversal, a pair of alternate exterior angles are equal, then the lines are parallel. If, when two straight lines are cut by a transversal, a pair of alternate exterior angles are equal, then the lines are parallel. If, when two straight lines are cut by a transversal, a pair of alternate exterior angles are equal, then the lines are parallel. Stay with me. So we got these two alternate and exterior angles. We're told they're equal, right? Well, let's call this angle 3. Let's call this angle 4. Thoughts on 1 and 3, class? They're equal. Vertical angles. Thoughts on 2 and 4, class?
Equal.
Very equal. So angle 4 and angle 3 are equal to equals. And if quantities are equal to equal quantities, they're equal. So angle 3 must equal angle 4. Well, what kind of angles are 3 and 4, class? Alternate interior angles. And if alternate interior angles are equal, class, then lines are parallel. So if alternate exterior angles are equal, because we can get alternate interior angles equal, lines are still parallel. We'll have to pick up with more in our next lesson. Your homework for this evening. Homework for this evening is to do page 70, number 2. Page 70, number 2. It's some numerical exercises. Actually using numbers for a change. What in the world? All right, so page 70, number 2, and we'll look at those and some more numerical exercises, in fact, in our next lesson. And then also do handout 12. So page 70, number 2, and then for our proof over the weekend, handout 12. I've given you nearly all the statements. I've given you barely any reasons. Okay, so kind of lopsided the information here. Complete that. We'll take a look at it Monday. You are dismissed. Have a great rest of your day and a great weekend.